Welcome back. In this module, we will explore propositional logic. Here are the objectives for this module. We're going to start out by describing what are propositions, what are logical connectors, and then building that up, looking at things like inference, soundness and completeness, and so on. Now, how does this fit into the concept of the agent? And let's review this notion of an agent. So we have an agent, and it interacts with its environment. And this is a very common paradigm in artificial intelligence. And it can perceive its surroundings, and then it can take action based on those perceptions. And to do this, we can think of this as there's two systems, and this is analogous to what we do as humans. We have a system 1, which is thinking fast, and we have system 2, which is thinking slow. Now, what are these good for? Well, system 1, we can rapidly perceive the information around us. So if you look at a stop sign, right away you see the color red. You know it's red, you don't have to think about it too much. In much the same way, perceptual models such as convolutional neural networks are really good at making sense of their surroundings. Now, if I give you, say, a math problem that's very difficult and you have to work your way through it, you're not going to use system 1. You're not going to see a complicated algebra or calculus problem and instantly be able to come up with the answer. Instead, we resort to system 2. And this is where we're doing reasoning. So it's much slower, but it's reaching conclusions based on inference. And a great example of this is propositional logic. So how do we think about the logical agent? Well, again, here we have the agent, and it has a knowledge base, and it has an associated inference procedure. And the goal here is the agent wants to reason about the world with propositional logic. So the knowledge base can consist of logical statements that are thought to be true about the world. And we could think of these logical statements as being instantiated from some sort of perceptual model. Complementing that is the inference procedure. And the inference procedure is designed to draw conclusions from that knowledge base. And so that is essentially your system 2 right there. So that's it for the module introduction. Stay tuned for some exciting lessons on propositional logic. Welcome back. In this lesson, we will give a brief introduction to propositional logic to help hone some intuitions about this way of reasoning. So by the end of this lecture, you should be able to describe what a logical proposition is, as well as the major logical connectives that we'll be using throughout the module. So first, a proposition is simply a statement that could be either true or false. So here are some examples. The sun is hot. The earth is made of cheese. 2 plus 2 equals 22. And the 1000th decimal place of the digit pi is 9. So whether any of these statements is true or false, it doesn't matter. It's that they can be either true or false, one or the other. Very straightforward. That's what a proposition is. Now, if these are propositions, let's give some examples of things that are not propositions, and hence we cannot model them directly in a propositional logic. Are you bored? This is not a proposition because it's an open-ended question. So it can't be true or false because the question itself is not true or false. You can answer it. A statement such as, I am bored, or you are bored, could be true or false. But as a question, that is not a proposition. It is open-ended and it can't be defined as true or false. Please go away. This is a command. So this cannot be evaluated as true or false either. She loves me. So again, we can't evaluate this directly as true or false. X is an integer. Now this one is getting a little bit different reason from the others as to why this is not a proposition. This is not a proposition because X is a variable symbol. it is not defined. So as a result, we cannot evaluate the truth of the statement for this reason. This sentence is false. Now this is an example of a contradiction. The sentence itself, if it was true, it would mean that the statement that the sentence is false is true, which means that the statement is false. So it can't be both true and false at the same time, is what's called a contradiction. For that reason, this final item on the list is also not considered a proposition. So connectives. So these are the core logical connectives, and from these you can create the other major logical connectives. And the first one is not. So the negation of a proposition is simply the opposite. So if we say 2 plus 2 equals 22, as we saw in the last slide, the negation not 2 plus 2 equals 22, that is going to be true every time the first statement is false. Conjunction is simply and. Two propositions are conjuncted together, and they both have to be true for that entire statement to be true. So I am wearing a shirt and I am wearing a jacket. Disjunction. At least one of the statements needs to be true in order for the entire statement needing to be true. So I either have blonde hair or I have brown hair. The next are a set of connectives that can be derived from the ones we showed you on the previous slide. And the first one is very commonly seen as implication. And you often hear that as in terms of if, then. If the first statement is true, then the second statement must also be true. If you study this class, you will get a good grade, is an example of an implication. A biconditional is an implication that is going in both directions. So it can be thought of as an if and only if statement. So if and only if I drink water every couple of days, I will survive. I will avoid dehydration. That's an example of a biconditional. So here are some English language examples. So we have two propositions. 2 plus 2 equals 5, so clearly false. And the sun is hot. So for most definitions of hot, we would say that's true. So we can form the following propositions. It is not the case that 2 plus 2 is 5. So this is a negation. 2 plus 2 equals 5, and the sun is hot. That is a conjunction. Of course, since 2 plus 2 equals 5 is false, that whole statement is also false. 2 plus 2 equals 5, or the sun is hot, so if we define sun is hot as being true, then this whole statement is true regardless of what 2 plus 2 equals. If 2 plus 2 equals 5, then the sun is hot. Now, the truth of this is a bit more tricky because we might see this in everyday life and think, wow, that statement is false because 2 plus 2 does not equal 5. However, if 2 plus 2 equals 5 is false and the sun is hot is true, then the whole statement is true. Because if the premise of a implication is false, then really the rest of it doesn't matter very much. 2 plus 2 equals 5 if and only if the sun is hot, and this is an example of a biconditional. Now, while the statement above it is true, if 2 plus 2 equals 5, then the sun is hot, we also have to have the other direction being true for the biconditional to be true. And the other statement would be, if the sun is hot, then 2 plus 2 equals 5. So if the sun is hot is true, and 2 plus 2 equals 5, that if-then statement, that implication is false. So the entire biconditional at the bottom of the slide there is also false. So this wraps up our introductory lecture on propositional logic and the connectives. Stay tuned for more content. Welcome back. In this lecture, we will further explore propositional logic, focusing on truth tables and natural language interpretation of propositional statements. Here are our objectives. All right, so the truth tables. So let's talk about the major operators for propositional logic, and the first one is not. And how does that truth table function? We will use, in general, lowercase symbols to represent our propositions in this lecture. So we have the statement at the top there, not A. And so we can see in the truth table that simply the negation every time A is true, not A is false, and then the other way around as well. And the next major operator is the conjunction, which is and now we have propositions A and B. And the only time that A and B is true is if both A and B together are true. It is false everywhere else in the truth table. The third operator is or. And or is only false when both propositions A and B are false, as seen in the top line. And is true everywhere else, because only one of the propositions needs to be true. Implication, if then. So this is a bit different from the others. And we notice that we have the antecedent, which is what A is called. So A is called the antecedent. And B is the consequent. Okay, and that's easy to remember because consequent is the conclusion of the implication. You could think of it in that way. Well, anytime the antecedent is false, the whole thing is true. Because what's that saying is, if A is false, B may or may not happen. So if we think of something like, if the sprinkler was on, then the grass is wet. Well, the sprinkler could be off and the grass might be wet because it rained. And that's okay. If the antecedent is false, the statement is always going to be true. Now, it's when the antecedent is true, then we have something a little bit more interesting. If you have the case where the antecedent is true and the consequent is false, the entire statement is false, because this is saying that if A occurs, then B must occur. And so if we have the sprinkler was on and the grass is not wet, then the implication is false. Likewise, if both A and B are true together, the entire statement is true. So implication gives us a nice opportunity to explore this idea of logical equivalence. So you may recall in an earlier lecture we talked about how conjunction, disjunction, and negation were kind of the core logical operators, and other operators such as implication could be derived from them. Well, in this example, I will show you how implication is actually equivalent to a combination using negation and disjunction. So here we have columns A and B, which are the two propositions we're combining with the implication, and we repeat those columns below. Same initial truth values. So to show that these two formulas are equivalent, we now take the negation of A, and so everywhere A was false, it becomes true for not A, and it's false otherwise, so it's flipped around. Now we combine that with B using a disjunction, which is what we have here. So we have these two truth values for not A make this whole thing true. So this is true and this is true. And this is the only line that ends up being false because both not A and B are both false. And finally, the last line is true because we have B is true. And so as you can see that the formula if A then B is logically equivalent to not A or B. So now let's consider, how do we take natural language and transform it into logic? So let's start with each operator. First, let's talk about conjunction. And what often happens in natural language is the use of the word "and" could have a potentially temporal connotation. And here's an example. The kid threw the stone and broke the window. Now, the kid threw the stone and the window broke are two propositional statements. But our common understanding adds this aspect of a cause and effect. I think most everyone would read this sentence and would think about a young kid throwing a stone and the stone hitting a window and breaking it. Whereas the logical understanding is the window broke and the stone was thrown. There is no relationship between these two events. It's just they're two things that happen in the world at the same moment. And this is due to one easy way to detect in English language if what you're transforming can be directly represented with the same logical statement is think about this property called the commutative property. And if our understanding is not commutative, then it can't be translated directly into logic using that operator, or using conjunction in this case. So the way we can understand this is, let's flip it around. Does a sentence convey the same meaning? The window broke and the kid threw the stone. And that does not have the same meaning. You hear that sentence, you think about, well, there was a window that was broke and then a kid threw the stone. It doesn't imply, as the sentence in the slide does, that the kid threw the stone and it hits the window and breaks it. The logical understanding, you do have this commutative property. If we talk about the window is broke and the stone was thrown, and both those things happen, but they're unrelated, they just both happen together, it doesn't matter the order in which you express them. And this makes sense because if you remember our truth table for A and B, it makes no difference the ordering of A and B. So disjunction, the common thing we see in language is there is an implicit exclusive or. An exclusive or means that we're only allowing one of the two items that are disjuncted together to be true, but not both together. And an example of this is you will win or I will win. And in most cases where you hear this sentence, you're not going to assume that both you and I will win together. There is an or there. It implies one or the other. But in the common understanding is that only you or I will win, as opposed to the logical understanding is one or both of us will win. And as you see in the first case, there's this exclusivity. Only one will win. Where in the standard definition of disjunction, it's okay if both of the items in the disjunction are true, the statement can still be true. That, as you saw in our truth table, is how disjunction works. So the next operator to consider when going from natural language to logic is the implication. And a key difference between logical understanding of the implication and a natural language one, as we mentioned earlier, is that if the antecedent of your implication is false, the precondition, the thing that causes the consequent, then in most common natural language understanding, we consider the whole statement to be false. However, in logic, anytime the antecedent is false, that whole statement is true. And that's what's called being vacuously true. And so here's an example. If 2 plus 2 equals 5, then the moon is made of cheese. This is actually a true statement. And the reason being is that 2 plus 2 doesn't equal 5. And if we think about it logically, in all the worlds where 2 plus 2 equals 5, it could be that the moon is made of cheese. But as that is a false statement, the whole thing is vacuously true. Where in normal conversation, we would think that the whole statement would be false. So let's examine why, looking back at our truth table for the implication. So again, this is the antecedent, 2 plus 2 equals 5. Logical proposition, we can assign a truth or a falsehood to it. Here is our consequent, also a proposition. The moon is made of cheese. Here is our truth table for the implication. And as we can see here, regardless of if the moon is made of cheese or not, anytime that antecedent is false, that whole statement has to be true, because that initial condition never holds. So this concludes our lecture where we looked at translating from natural language to logic, as well as covered the truth tables of the major operators. Stay tuned for more content. Welcome back. In this lecture, we will look at how to compute truth values in propositional logic. And here's our lesson objective. All right, let's do a little warm-up example. So let's consider the following logical propositions. We'll say proposition A, logic is fun, B, logic is boring, and C, logic is easy. And so we will call A, B, and C propositional variables. And we will consider the following truth assignment. So we will assign these propositional variables to be either true or false. So we'll say A is true, B is false, and C is true. And so how do we evaluate the following statements? Logic is not easy, or if logic is fun, then it is easy and not boring. So here is our statement. And just like in math, or in arithmetic rather, the order of operations is important. So to make this a little easier, let's rewrite our statement using parentheses. And here is that. Okay, so recall, here's the definitions of A, B, and C. Here is our statement rewritten with parentheses. And here is the same statement, but now we use the variable symbols A, B, and C. And so we can look at what is in the parentheses and evaluate what is, what has the fewest operations first. So we'll start with evaluating not C, and we'll go from there. Now the order of operations for doing this type of evaluation is, if there's no parentheses, you always want to start with negation, then go to conjunction and disjunction, followed by implication, and finally the biconditional. So here we can go and we can plug in the initial truth assignments to the variables, so the same statement as above. And we can right away see that not true can be replaced by false. So we have that, and we also have the negation not false can be replaced by true. So now what we have here is we have the statement that's a conjunction of true and true, and if true and true are conjuncted together, the result is also true. Now we have false, or if true, then true. If true, then true resolves to true as well, because both the antecedent and consequent are true. And if you connect true and false with the disjunction, the result is true. So let's get some additional terminology here. So formulas, so the logical statement we just showed you is an example of a formula. And then true and false, those are propositional constants. They don't change. Likewise, we have A, B, and C, as we stated earlier. These are our propositional variables. And of course, at this point, we're quite familiar with the major logical connectives of negation, disjunction, conjunction, implication, and the biconditional. We've also added parentheses, which are auxiliary symbols. They don't perform a logical operation, but they can specify the ordering of operations in case we want to do something beyond the standard order. So we can also formally define a formula inductively as follows. So every propositional constant or variable is a propositional formula. And if A is a propositional formula, then not A is also a propositional formula. So imagine here, A could be anything that results from this definition. And likewise, with the logical connectors that allow for the connection of two logical statements, we can say if A and B are propositional formulas, then A or B, A and B, if A then B, and if and only if A then B are also propositional formulas. So we can look at the evaluation of a logical formula using what's called a construction tree. And this is a tree-like directed graph structure, and is created by every leaf node is labeled by a propositional constant or variable. Propositional constants and variables label only the leaves. Every node labeled with negation has exactly one successor node. And finally, every node labeled with any of the other logical operators has exactly two successors, one to the left and one to the right. And of course that makes sense because each of those logical operators require two propositions. So here's an example. So let's consider the following formula. P or the quantity not Q and not R, then not R. So first let's make the leaf nodes with the propositional variables. Now we include R twice because it appears two times in the formula. So then we add nodes for negation. And then since the second R has two negations, it gets another child node. Now we add another node for conjunction because Q and not R are combined together. And we add another node for negation because the quantity Q and not R itself is negated. And that is combined with P with a disjunction, which gives us this node. And finally, that is combined by implication with not R. So this structure can then be used to evaluate the truth or falsehood of a logical formula. And stay tuned for more content as we continue to explore propositional logic. Welcome back. In this lecture, we will discuss inference and propositional logic. And here's our lesson objective. And so we say a propositional formula B is the logical consequences of propositional formula A1 through AN. Basically, if every time A1 through AN is true, then B must also be true. And this is the key takeaway sentence right there. Now, why is this an important problem? Well, A1 through AN, we can think of that as existing knowledge. And we could think of B as a query. And we want to see if B is true based on this existing knowledge we know of A1 through AN. A1 through AN can be also known as assumptions, and B is often referred to as the conclusion. And so how do we check? Well, a really easy way to check is create a truth table for A1 through N and for B. And whenever A1 through AN are all true, then B must also be true. And that's the check that needs to be performed. So let's give a quick example. So we have two formulas in the assumptions, P then R and Q then R. And we want to check P or Q then R. So here's the associated truth table. So we have columns for the two assumptions, P then R and Q then R. And then we have an extra column there, working through the query. But here is the final answer. Okay? So we look every time when the assumptions are both true. So we have true here, this guy has to be true. True here, that guy has to be true, and it is. True here, true here. This guy has to be true. True here, this one, and same thing with the last one. And so we can conclude that the statement can be concluded from the assumptions. Now, this seems like something fairly easy to do, but let's look at the complexity. So is this sufficient? And the answer is actually no. And why is this? Well, it requires an enumeration of all truth assignments. So when we do these simple problems in these slides or in the text where we only have 3 propositional variables, we can write it out and we can solve, and we can even imagine doing this with more. But what if you get to hundreds or thousands or millions of propositional variables? Well, now we're getting into an exponential time operation that could take years and years to compute. So stay tuned for more content and we'll look at how to resolve this problem. All right, welcome back. In this lecture, we will look at inference rules. Here are the lesson objectives. Now, if we recall, a logical consequence is defined as when you have a set of assumptions, A through N, which is maybe your existing knowledge of the world, we say that B is a logical consequence if every time A1 through AN are true, then formula B is also true. Now, if you do this evaluation using truth tables, then you're quickly going to run into trouble when you have more and more propositional variables. You will run into an exponentially large truth table. So this is not good. We want to look at ways to avoid this. So we have this idea of a proof rule or inference rule, where we maybe have some information that we know that, hey, given a certain propositions that are true, something else will also be true. And we can think of a very easy example of this would be that if we have, let's say, A is true and B is true, well, we can conclude A and B is also true. This follows right from the definition of a conjunction. And so we can write a bunch of rules like that to help us with the inference process. Now, we could create a set of these rules, and they are called logically sound if they're correct. So the one I just drew on the slide for conjunction is an example of a logically sound proof rule because it follows right from the definition of conjunction. Anything that we conclude resulting from that rule is going to be correct, and we can evaluate that and prove that it's correct based on the truth tables. Now, we say something is complete when we can be sure we can derive every possible outcome. Now, if I gave you only a logical or only a proof rule for conjunction, it won't allow you to do any additional reasoning if negation or disjunction are present. But for everything where the focus is on that use of conjunction, it'll still give you the right answer. So a set of rules is sound if for each rule the conclusion follows the premise and is done correctly. And again, we say it's complete if all of the logical consequences can be derived from one or more of the proof rules, and when we say more than one proof rule, we could chain them together and apply them iteratively. So we'll wrap up the lecture by talking about one of the most important proof rules that's widely known, and that's modus ponens. And that is if we have P and also this assumption P then Q, then we can derive Q. And this, just looking at it, makes a lot of sense. It follows directly from the intuition of an implication, and it is correct based on the truth table definition. So example here of this being applied in a situation with propositional variables, we have raining, and then if raining, then wet grass, we can conclude wet grass. Now the following is not modus ponens, and we have A equals 2 and A plus B equals 5. Now, these are two statements, but we can't, they are not being combined together using any kind of connector. So we have three statements that are potentially all different. A equals 2, A plus B equals 5, and B equals 3. Seeing this and thinking it's right, we only believe that because of our underlying knowledge of how arithmetic works. But from a purely logical perspective, this is not a valid proof rule. So with this in mind, let's revisit this concept of the logical agent. So the logical agent has a knowledge base and an inference procedure, and often what we see in propositional logic is the knowledge base is a set of propositional formulas, our assumptions about the world. Where the inference procedure we can view as the set of rules that is used, or inference rules, used for drawing conclusions about those propositional formulas. So thank you for tuning in, and please check back for more content.